Okay, hi everyone. Welcome. So I'm just going to give it a few minutes just to see if people need time to log on. As a like heads up, there is like a 10-second delay on my half. So if you type anything in the chat and I have like a question, there will be a lag just by the time I see it and by the time it's by the time you are actually seeing me answer. So yeah, I'll just give it a few more minutes and then we'll go ahead and start the show. And feel free to use the chat right now throughout the show. Just you could say hi, or how I said, ask questions on the chat. I don't think you can actually use it off of a cell phone, but you're able to use the chat if you're viewing off like a laptop or a computer or something. I'll give it like one more minute and then I'll go ahead and start. Just in case you're like just signing on, I'll be starting soon. Okay. Yeah, I'll go ahead and start. Hi everyone. My name is Lizette Villafania, and I am a second year astronomy PhD student at UCLA. I'm one of the planetarium coordinators, and there's five of us total. And if you're not familiar with the UCLA Planetarium, it is purely a grad student run, I guess, like organization, or it's purely grad student run. And what we do is that we put on these public shows. We just want to kind of share our love for astronomy and knowledge for astronomy to like a general audience. And typically these shows are in person. We have a small little planetarium dome on campus, like the projector, and we have these shows every Wednesday. However, due to COVID, we kind of transitioned back and forth given how cases are doing in the area. And because of COVID, we have transitioned to this online format and use YouTube Live. And if you ever miss the shows, you can watch them afterwards. They are posted to our channel. And we always promote our shows on either Twitter, we have a Twitter profile, we have a Facebook as well, and we also have a website. And so I'll go ahead and get started with today's show. As I mentioned, if you were here 2 weeks ago, 2 weeks ago we had a show that was highlighting the work of historic Black astronomers and physicists, and it's also on our channel. As I mentioned, we always post them afterwards. And just to kind of recap, if you did not watch that show, this show is kind of part of a series of these like inclusivity shows that some of the coordinators, including myself, are trying to organize and get set up annually. And in this today's show, we'll be highlighting some of the work of Black astronomers within the Los Angeles area, whether they are currently here studying as graduate students or grew up in the area and are now doing their graduate studies elsewhere. And with that, I'll also give a brief promo for this week. Usually we only have one show a week on Wednesdays. However, today's show is on a Monday because of some technical difficulties. My laptop broke the week we were supposed to have it. So we are wrapping up the Black History Month on a Monday instead. But our Wednesday show this Wednesday at 7 will be celebrating Women's History Month. So essentially, we are kind of creating the shows just because I personally think it's like important for future generations to like see themselves in astronomy, and I do think that it's like our responsibility to set up a new like a community that is grounded in respect and diversity, as we mentioned here on this message. So for today's show. I'll kind of be taking you on a tour of the universe starting from here in LA and kind of expand out. And in that process, give some details of the cool science that we have six Black astronomers and physicists from the area, as I mentioned. If you are follow our Twitter page, we gave them individual shout outs. I definitely would recommend to check out those threads. But I'll start here in LA and then kind of zoom out and give you a picture of the universe and the contributions of the students that we are highlighting today. And I also, with that, want to give a shout out to Isabel. Isabel is a third year graduate student as well and one of the coordinators. This was the setup of the slides was her idea, and I think it's really cool. So I do not want to take credit for it myself. And so, as I mentioned, giving you a brief tour of the universe starting here in LA. As many of you might not be watching from LA, which is a cool part about YouTube Live, but starting here in LA at UCLA, we're on the west side of Los Angeles. And as you expand out, of course, you, we are, and we live on planet Earth with our moon orbiting us, right? An interesting fact about our moon is that it is pretty large for given our planet size, and there is a theory of there is the idea. The theory behind the moon forming, right, is that there was some kind of collision on Earth and it impacted Earth and then became its own moon. So that's pretty cool. Just as I said, I kind of want to drop small bits of science as I can throughout this tour. And at any point in time, if you have any questions, please feel free to ask in the chat. I'll be moderating it at the same time. As I mentioned very early on, though, there is a 10-second delay with the way the live stream works. So if I don't see it and I take a little bit of time to get to it, that is probably why. Beyond Earth, we then get into our solar system. And if you remember, like when you were a kid, maybe you learned the like mnemonic that was just like, my very educated mother just sent us some pizzas. But Pluto is no longer considered a planet. It's considered a dwarf planet. It doesn't clear up enough. It doesn't clear out its orbit out. And once we discovered there was other like comments of its size, it was part of the reason why it's no longer considered a planet. But yeah, you have Mercury, Venus, Earth, which is us, right? And then very educated. I always have to do this. Mars and then Jupiter, Saturn, Neptune, and Uranus. So going into the work and within this tour of the solar system, I do want to highlight some of the work that the astronomers we're highlighting today have worked on. And starting with our first astronomer, her name is Angelina Gallego. She is currently a grad student at the University of Minnesota in Twin Cities, but she grew up in South Central LA with her grandma, sister, and older brother. And she is a first generation American, first generation college student, graduate student as well. And her mother and grandmother immigrated from Belize, and she always loved science. It was one of her favorite subjects growing up. But when she went to visit Catalina Islands in seventh grade, she saw the sky without light pollution for the very first time and instantly fell in love with the universe. Ever since that day, she knew she wanted to study space for the rest of her life and has worked hard to make that become a reality. I found her words really inspiring. I really like that. And one of her first projects that she worked on while she was an undergrad involved the planet Jupiter. So, cool fact, if you keep up with like NASA missions and any of that sorts, there is currently a mission that is planned to Europa, which is one of Jupiter's moon. It is planned to launch in October 2024, and it's called the Europa Clipper mission. It's meant to study Europa, which is one of Jupiter's moon, through a series of flybys around Jupiter. So what that means is that it won't be orbiting Europa, it'll be orbiting Jupiter, and it'll just be flying around, right? And then get images of the Jupiter's moon Europa. And this is like a really exciting mission just because there's strong evidence for an ocean liquid water to exist beneath the crust of Europa, and it could possibly host some form of life. So with that being said, Europa is only going to use Jupiter as a calibration. It's not the primary mission of the Europa Clipper mission is to observe Europa, and that's the science target, not Jupiter. But it'll have to take images in order to calibrate itself. So the work that Angelina did during her undergraduate was a proof of concept kind of project. Basically, what she did was that she used images taken from the Cassini flyby mission and wanted to show that even though Europa Clipper will be studying Europa, we can use those calibration images that it will take of Jupiter to also get science out of it. So what she looked at in particularly was she used the images that the Cassini mission captured of Jupiter, and analyzed the motion of the clouds in those images to try to measure the wind speed. And the what she found was that the fastest winds are happening at the equator, which was expected, just because there's a jet in that area, and she found the highest wind speeds were 20 degrees latitude in that near the equator, and the highest point of wind speeds were around 150 meters per second, or 100, like between 130 and 150 meters per second. And depending on the filter that was used, I personally think that is insane. When I go to Joshua Tree and there's like 30 miles per hour wind, I really can't handle that. So the slowest point of wind that she found was that it was around 50 meters per second. And I think this is really cool, just because it shows how extreme this is the first glance we're getting at how extreme the universe really is. And I think that was one of the things why I like astronomy. Most of the universe is very extreme. So that was one of Angelina's first project. And continuing on with our tour of the universe, she also used Cassini data to study the dynamics of the hexagon on Saturn. So that's shown here on the left side, right there, that hexagon. This hexagon is a six-sided jet stream at Saturn, located at Saturn's North Pole. And this movie is made from images collected using Cassini's imaging cameras. And this hexagon is a massive hurricane that's centered on the North Pole with an eye about 50 times larger than the average hurricane eye on Earth. So again, how I said, it's really looking at the weather of other planets in our solar system is just like the tip of the iceberg of how like extreme the universe is. And these red ovals you hear correspond to small vertices, that and some spin clockwise and counterclockwise. So if you're unfamiliar with like what a vertices is, it's just think of like a whirlpool. If you ever like were a kid and would like play in a pool and like just go around to create a whirlpool, that was one of my favorite games. That's what you can imagine these red dots are. And inside the hurricane, there are these vertices, right? And there's smaller features. If you can look at it, they kind of start to blend in. So that's because the jets start to go around in this hexagon, kind of like if it were on a racetrack. So that was something really interesting we found with the Cassini mission, because we hadn't imaged it like this before, Cassini. And the biggest vortices, this big one right here on the lower right corner, right there, that's kind of like whitish. That one is the largest of all the vortices, and it spans about 2,200 miles, which is twice the size of the largest hurricane recorded on Earth. Again, very extreme weather on these gas giants. And then this movie here, what I did also want to note is that the different colors correspond to different wavelengths. That is something that is common. Like in astronomy, we will use different colors just for like data visualization. And but to the human eyes, this hexagon and the North Pole would actually appear in tones of gold and blue. And continuing on with some more kind of the tour of the solar system and just wrapping up the highlight of the work Angelina does. As I mentioned, she is currently at the University of Minnesota at Twin Cities, and her current research project has now kind of shifted from the Cassini mission data and these gas giants to now she is focusing on solar physics and studies the interplanetary shocks and Earth's magnetosphere. So the sun, right, the outer part of the sun's atmosphere is very, very hot. It's much hotter than the other parts of the sun, and which is called the corona. And that's a part of the sun that, if you've ever seen a total solar eclipse, that you're able to once it's in totality and you see the outline, that's the corona, right? And that has very, very hot temperatures, and it releases these energetic particles. So the sun constantly has these things called has these bursts of like these energetic particles, and it's called the solar wind, and it interacts with all the planets and their magnetic field. And that's actually like why we get aurora, right? So we see those aurora, the different colors of lights in the poles, right, in North Pole and South Pole, because our magnetic field has these like gaps in the poles, and the energetic particles from the solar wind enter our atmosphere through those gaps, and these energetic particles interact with other particles in our atmosphere, like oxygen, and that's what gives those like pretty green, purple colors of aurora. So, uh, essentially, any kind of study within astronomy that's like has to do with solar wind and the sun is like solar physics. Solar terrestrial physics is with Earth, right, or space physics, and that's currently the work that Angelina is looking into right now at the University of Minnesota. And continuing on with our tour, kind of backtrack a bit into the solar system and look at Mars. To highlight one of our very own graduate students at UCLA is Dakota Tyler. He is a second year in my cohort. And also, brief, interesting fun fact, I will try to mention a bit of their like intro to astronomy as I can. As I mentioned, we did highlight them on our Twitter. You could check out those threads as well. But Dakota has a non-traditional path into astronomy. He was a strong safety for the University of Kentucky, and then a knee injury ended his football career earlier, and he was left looking for something else, like another passion, and that like sparked his interest, and that was the universe. So he then went and started from the basics at community colleges and started with algebra and built up, and now is here at UCLA. And some of the research he did during his undergraduate at the University of Cincinnati was involved analyzing Mars' atmosphere during a global dust storm while he was working at the NASA Goddard Space Flight Center. And the cool thing is that, so if you all, maybe you all are very familiar with the Martian storms, just because it has come out on movies like The Martian. So Mars does have a lot of has a lot of wind storms, and even with one of the rovers that was there, I believe a couple years ago, there was a very intense windstorm and it covered one of the rover solar panels and it couldn't charge for like a while. I can't remember when that dated back to. I just know that's like a random fun fact I remembered off the top of my head. So yeah, essentially there's a lot of stars on Mars, right? And sometimes they'll coalesce and like combine basically to form these larger storms that can cover the entire planet. And it's actually visible too. Like if you look up like NASA, like Mars storms, there's some pictures that'll show you like before a global storm and after, and you can see it's like a storm covering the entire planet. And so what Dakota did was that he used carbon monoxide or CO in the atmosphere of Mars to probe the different temperatures during the global storm. Again, just interesting. This is part of planetary like sciences and like just discovering the different weather on other planets. And how I said, I think it's very cool just because the weather on other planets is very extreme and a lot of astronomy is very extreme. So continuing on our tour of the universe, once you leave our solar system, you have other star systems, right? And this is related to some of the early work Dakota also did. He looked at a specific type of star, young variable star called Titori stars, and he was modeling their accretion disk. This kind of work helps us understand planetary formation. These young stars, basically, the accretion disk means that it just has like material that's like accreting or gathering around it, right? And um, you can, because there's like very young stars and it's forming planets, you can also sometimes get these like planets sweeping out material or anything cool like that. And this was some of the early work that Dakota did, and by doing this work he kind of learned where his interests really lie in exoplanets, right? And as you can see here, that's the next stop in our tour of exoplanets. So essentially, as a recap, we live on Earth, right? And then you go out into our solar system, and outside of our solar system, you have more star systems. And an interesting fact too of like in regards to exoplanets studies, it's a very active area of research in astrophysics right now, because it's a very cool idea to think that it's only been a couple decades since this has been an area of astronomy research. And the first exoplanet, so we for a long time believed that there was other planets other than outside of our solar system, but we didn't have evidence until the early mid 90s. And since then, now there's about over 4,000 exoplanets that we have discovered. And a fun fact, which is that all these exoplanets are within our own Milky Way galaxy. We haven't looked beyond that yet, to my knowledge. There may be like maybe a few rare cases, but to my knowledge, all the exoplanets that have been detected have been only within our Milky Way. So that's why this is the next stop in our tour of the universe, since the exoplanets still are within our own galaxy. And so some of the work that Dakota got into towards the end of his undergrad was started at an REU, or a research experience for undergraduates at Harvard, and he looked at a helium absorption line, that lets you look at the star essentially. So you have this, if you look at the variability or how the helium absorption line changes in the star, that can help you probe the exoplanet's atmosphere, because essentially you have this planet that's orbiting its star, and as it orbits its star, the star absorbs some of the helium atmosphere from the planet. And going into this as well as that, one of the interesting like findings with exoplanets that astronomers had in the very beginning was that we detected something called hot Jupiters. And these are Jupiters that are very close to their star. So before we had discovered any of these exoplanets, we thought we had a really good idea of planetary system formation, and that we thought that most star systems would be like our own solar system. And we thought that, we have all these gas giants like Jupiter and Saturn beyond like the frost line, right? And that anything that was composed like that would be formed outside of that frost line. Then, to our surprise, we found a lot of hot Jupiters, and these are Jupiter-sized planets that orbit their star within 1 or 2 days. So this is the kind of planet that Dakota is looking at, and he is trying to see, he's probing the helium absorption line to see how this planet is losing mass over its lifetime, because essentially as it's orbiting so close to its star, it like gets all this atmosphere pulled off and it loses its own atmosphere. And one of the cool things is that because they orbit its star so within it, the orbit time of around its star is so small that it allows them to observe it more often and really try to understand like how exoplanets form, and the demographics of it. So exoplanet demographic just kind of refers to the, I guess you can see like the distribution of like exoplanets, and understanding how they lose their mass might help with understanding the exoplanet demographic. And so continuing on with our tour, still within our galaxy as well, is our next graduate student we would like to highlight is Jason Williams, who is a graduate student at USC, and also the Carnegie Observatories. And his path in astronomy started when he was an undergraduate at Columbia. He emailed about 20 physics engineering professors and only 2 replied. I really wanted to include that in this talk just in case there are like any undergraduates or any astronomers that are any undergraduates or students who are interested in astronomy, and to kind of know that all it really takes is one yes, like anything else in life, and to really go for it and reach out to all these professors, like Jason did. And one of those 2 professors who replied was ended up being Jason's mentor, named Professor Chuck Haley, who was co-lead on a balloon-borne instrument called GAPS that seeks to indirectly detect dark matter. So indirectly means that you're not detecting the dark matter directly. You're doing it through other methods like looking at the radiation left over after it interacts with atoms in our atmosphere. So this was really exciting and it was cutting edge, and Jason mostly did hands-on work in the lab, which is what he enjoyed, and he ended up staying in that lab throughout his undergrad, and by the end of it was fully committed to go to grad school. And once he was in grad school, he kind of he shifted, from dark matter experiments to into instrumentation, or the building of instruments for astronomy, and specifically related to exoplanets. And as I mentioned, he is a USC graduate student, and his research advisor is a staff member at Carnegie Observatories. And he is the lead instrument designer for a new instrument named Henrietta, that's meant to look at the atmospheres of transiting exoplanets. he's really enjoyed working on this just because they're trying to break ground on a type of measurement that's been notoriously difficult to do from the ground because of Earth's turbulent atmosphere. So essentially, all these types of observations are very hard to do from the ground because our atmosphere gets in the way of these observations. That is why we do put telescopes into space, just because it makes certain observations easier to do, especially like in the infrared part of the spectrum, infrared light. And a good analogy he gives, Jason gave us about what his instrument is trying to do is basically, and why these are like these measurements are so hard to do is this analogy he gave was like, imagine you're inside imagine the Stadium, right? Imagine you're seeing the Dodger Stadium from space. And imagine the Dodger Stadium is well lit, the whole thing is lit up, and you're seeing this far from space in another star system. And then you do like you turn off one light out of the entire Dodger Stadium. It's still well lit up, but there's just one light been turned off, and you want to try to detect that variability. You want to try to detect that change in the brightness from space. So his words exactly are like, it's a lot of work, but he finds it fun for some reason. So it's really cool, groundbreaking work that Jason's working on, especially in the field of exoplanets. And one thing Jason wanted kids to know who might be watching this show about being an astronomer is that being an astronomer is the best parts of childhood and adulthood combined. You get to eat whatever you want and stay up all night, which is, when I read that, I thought it was really funny. I could confirm, there are nights, this was surprising to some of my friends that I told them I would stay up all night for observing runs, right? And then it like clicked. They were like, "Oh yeah, you can't see stars in the day, so our job is at night." And that is also true. I've observed with other friends, and we will unfortunately eat like Skittles and stuff, anything just to keep us up. So for little kids, it is the best of both worlds, as Jason mentioned. And continuing on with our tour of the universe and graduate students, highlights as well is our very own Ronald Lopez at UCLA. He so his journey into astronomy as well was that he was really interested since he was little, and his parents would take him to Griffith and JPL open houses, anything astronomy they could really find. And he would go around saying that he was going to get a PhD in astronomy before he even knew what it was. He had a poster of Caltech in his room as a little kid, but wasn't able to take any astronomy classes until college. And um, when he went to Pierce College, actually, he wanted to take an astronomy class, but his class schedule wouldn't allow it. So instead, he asked the professor to audit the course and would meet with him weekly just to learn more about astronomy. And then he transferred to UCLA as an undergraduate and was able to experience what life was like as an astronomy. Uh, and because he entered as a transfer student, he felt like he started research a little late and wasn't ready for graduate school. So he took 2 years off to do more research and get ready for his PhD program. And during this 2 year time period, he did a few different projects. The first one was that he worked on theoretical exoplanet formation and studied how eccentric planets migrate. So eccentric is just like a part of their orbit. It just means that they're orbiting, right? And he was looking at that and seeing how they go from being eccentric to circular over time and what causes that. So eccentric, you can think of it if you're like on a plane, right? The circular orbit, and eccentric, you get more of like a tilt in the orbit as well. And then after that, he also worked on instrumental data analysis and trying to characterize instrument performance. And then he started to study the 3D structure of a nebula, but wasn't able to get the tools he needed to go deeper into the project. But he began to figure out more what he liked to learn about, and he liked the more technical, practical aspects of astronomy. And then he started his first year of grad school at UCLA and worked with the UCLA Galactic Center and was looking for binary star systems. So binary star systems, they're two stars that orbit one another, like and that you can have more planets orbiting those. So like if you ever watch Star Wars and Tatooine, that planet that has two stars, there are a lot of binary star systems that exist out there. So this is what Ronald first started to do as a graduate student at UCLA, looking for those looking for binary star systems in the galactic center with the galactic center group. And he worked on basically multiple projects, but he found his real interest was in astronomical instrumentation and direct imaging of exoplanets. That is something that is an active area of research here at UCLA. And so I just also wanted to include this kind of like trajectory, as you can see for all of them and most astronomers too. There's you kind of develop your interest for any future generations out there interested in astronomy. You don't have to really know what exactly is your thing. Like you kind of find it out by exploring different topics, as you can see. And so now what Ronald works on is this. Oops, let me go ahead and move on to the next slide. So if you can see here, right here, you can see this debris disk that's warped around HD 110058. So what Ronald is looking into right now, sorry, I just laughed just because sometimes whenever you're working with galaxies or different sources as an astronomer, it's just a whole bunch of letters and numbers, usually pertaining to the catalog or who discovered it. And it's a mouthful to say that once. So what Ronald is doing is trying to look at the possibility that a planet may have caused this warping around this debris disk. So there's basically you have this debris disk and it's just all warped. So that's pretty cool too. And he's also, as I mentioned, into instrumentation. So up here on the top is the Keck telescope, which are the University of California telescopes, also with Caltech located in Mauna Kea in Hawaii. And what Ronald is doing is he's designing a component for the OSIRIS instrument that will aid in calibrating the spectrograph. So OSIRIS is an instrument on Keck, the Keck adaptive optic system in the infrared. So that's what Ronald is currently doing now. So two different instrumentation astronomers that we've highlighted, which is very important. That is how we get progress in astronomy. So it's really cool that they are contributing to that part of astronomy. And continuing on with our tour of the universe. So as I mentioned, you have our solar system. Outside of our solar system, you have more star systems, and the exoplanets we have discovered are only within our own galaxy. And um, as you continue expanding out, I do want to give a bit more time to this slide just because it's very pretty. So you have all these star systems, right, moving randomly around each other, around the galactic center, and then you have our galaxy essentially. And our solar system is located in the outer edge of the galaxy, and that's actually why when you observe it, it's still observable right now, but it's better to observe around May, June, and if you observe um, the Milky Way, right? And you can see it as like a strip around. And the reason we see that is because we're on the edge and we're like looking into it. So it looks like a little pancake across the sky. So next, for highlighting the astronomers that we're highlighting is Leonardo Clark. Leo is a first-year graduate student here at UCLA, and he's done a lot of research. Very impressive. He did his undergraduate at the University of Minnesota, and also did some REUs or research experience for undergraduates at Wisconsin-Madison. And he was interested in space themed library books, documentaries, since he was a kid, and grew up in Minnesota, where in high school he had the opportunity to look into scientific research before starting college. And he's done a lot of work, a couple projects involving our Milky Way, and then other projects which I'll also be talking about outside of the Milky Way. So one of his first projects was involved looking at the stars that are called red clump giant stars at the edges of our galaxy, because he wanted to probe and investigate the distribution of stars, or how much, basically the population of stars at the outer parts of our galaxy. And that's because in other galaxies, what we observe is that there's most of the stars are in the center, and then as you go further out in radius, the number of stars decrease. So this project that he did involved using these red clump giants, and these are red giants, as they sound, that are burning helium in their core. So our star, our sun, is burning hydrogen right now in its core, and eventually, once it exhausts all the hydrogen in its core, it'll have a helium core, and it'll start to burn that, and it'll like expand, and into like a red giant. And don't worry, it will not be within our lifetime, but it will encapsulate some of the orbits of the inner planets. So Leo used these specific type of stars just because they can use they're good standard candle, what astronomers call a standard candle, and that just means that they have a property that makes their brightness specific to them. And that means that because the thing is that a star can look brighter, right? But it's only because it's closer to us, right? So if you have like two different, like it, and as an analogy on Earth, you have two different flashlights, right? But one is just naturally brighter. It might look less bright if it's very far away from you, right? So in astronomy, we use something called standard candles, and that just means that because we know how truly bright it actually is, we can determine its actual distance. So that is why Leo used these to try to figure out the population of stars in the outer galaxy, because it would be easier to figure out their actual distances. And within this project, he found that evidence for a break in the volume density, or how many stars were at the outer edge of the galaxy. So essentially, he did find this confirmation in the fact that as you go out in the Milky Way, there's less and less stars, which is a pretty cool fact that I actually wasn't as aware of before, too. And um, then another project he also did while he was an undergraduate, which involved the Milky Way, was to look. He characterized a filament, which was 14 degrees long, connecting three major star formation regions. And in the study, with this finding, they believe that this filament is part of the Sagittarius arm, one of the spiral arms in the Milky Way galaxy. And this study was also done in radio astronomy. That's because molecular gas clouds are basically just gas, right? Regular H2 emits radio waves that you can detect from the ground. And these radio observations allow astronomers to analyze the position and motions of these molecular gas clouds. And that's how they were able to characterize this filament that they found. And this study is important just because it may help contribute to our understanding of what drives vertical motion in our galaxy. So there's a lot of studies that look into the radial motion, or I guess you can think of like the horizontal part of it, right? And looks at those motions, but there isn't much as many studies that look into like the vertical motion and a part of the motion within the thickness of the disk, which is what Leo's project here did. So continuing on our tour, as I said, you have our solar system, then you have a whole bunch of other star systems with over 4,000 exoplanets known, an active area of research, and then you get to our galaxy, which we know. If you go beyond our galaxy, we have the local group. The local group is composed of, there's a few like dwarf galaxies around the Milky Way, right? These small little satellite galaxies. And then the nearest galaxy to us is called Andromeda, or M32, and it also has these small dwarf galaxies around it. And this is our local group. You can also see Andromeda out in the night sky right now as a fun fact. I'll put that out there. So then if you go outside of the local group, right, our local group lives in what we call the local supercluster, the Virgo supercluster. And basically that's our understanding of the universe. Then you have our local supercluster lives around other superclusters, and we now know that there are millions to billions of galaxies out there. So going into the branch of extragalactic astronomy, one of my favorite parts, maybe biased since I study galaxies, Leo also looked into something called green pea galaxies. So if you have not heard of these are galaxies that got its name from the way they look. They're actually blue compact objects. So they are blue, which means they are star forming regions. So in astronomy, there's a saying called red and dead. So like any galaxy that has a lot of red stars are dead. Just as I said, our sun will eventually go to a red giant. So older stars are red and younger stars are blue, and they're hotter and burning their fuel more. You can think of that because of, when you like heat, like I had explained this once to my brother, when you heat like a stove, right, you sometimes will see that orange if you have like those electric kind, right? So that's cooler, right? And even hotter temperatures are blue and white. So you get those out in space. And so these green pea galaxies are actually blue compact galaxies, but they're green. They appeared green in these images, as you see on the right hand side, that were taken by the Sloan Digital Sky Survey. And these were discovered in 2007, 2008, 2009, around there by citizen scientists in the Galaxy Zoo project, which I thought was really cool. So the Galaxy Zoo project was a crowdsourced astronomy project that invites people to help out with the classification of galaxies essentially. And so two citizen scientists found out these green pea galaxies. And the idea is that they have a lot of star formation rate, so they're forming a lot of stars, and there's an active area of astronomy research in regards to a time in the universe called the epoch of reionization. So history of the universe, you can imagine you have like the Big Bang, right? And then skipping a bit, you have what we call the dark ages, right? And then after the dark ages, you have the first stars that ionize the universe, right? So these stars, like our sun, are releasing light, right? And that's releasing radiation that ionizes the universe, and that's the epoch of reionization. It's an active area of research because we still don't really know when that happened, or what were like the sources of that. And the reason these green pea galaxies are interesting partially too is because they may have sorry, implications for the epoch of reionization, and they're often referred to as the best local analogs of the sources that probably did reionize the early universe. And moving on with our tour of the galaxy and some of Leo's current work. Leo is currently working with Professor Alice Shapley in the department at UCLA and looking at a part of the universe which we refer to as cosmic noon. So, cosmic noon is about 2.4 billion years after the Big Bang, and our current understanding is that the observable universe is about 14 billion years old. So this means that cosmic noon happened somewhere between like 10 and 12 billion years ago. And this is basically a time in the universe where star formation was at its peak. So a lot of galaxies were forming a lot of stars, and we don't see that in our local universe as much anymore. So it's an active area of research as well. And what Leo is looking into is trying to get more accurate metallicity measurements. So, a fun fact is that in astronomy, we refer to anything heavier than helium as a metal. So when you first hear metal, you are probably going to think aluminum or any other metal. But astronomers, as I've said, refer to anything heavier than helium. So carbon and oxygen are considered metals in astronomy because the universe during the Big Bang, there was mostly hydrogen and helium, and everything heavier was then created by stars. Anything heavier than iron, so stars can only produce up to iron, and anything heavier than that, like gold and any other like element, was created in a supernova explosion. So when the star died and exploded, that's where heavier elements were made. But essentially, that's what metallicity refers to. So when you're looking for metallicity, you're trying to find anything heavier than helium in astronomy. And what Leo is looking at is trying to get more accurate measurements of this metallicity around cosmic noon. And that's just to try to that will allow for better constraints on galaxy evolution simulations. So that's also an active area of research where we're still trying to understand on how galaxies evolve and become what we now know today. There was a lot of star formation, and now when you look around, there's not as much. And it's just an active area of research that's really cool as well. And I, from today. I don't know what the chat comment means, but feel free to ask any questions in the chat at any point if you have questions. But continuing on our tour of the universe, so as I mentioned, it goes our solar system, within our solar system, and then outside of our solar system is what I mean. Within our galaxy, you have other star systems, which we found over 4,000 other planets within that area. And then outside of our Milky Way galaxy, you have the local group with Andromeda and other dwarf galaxies, as well as our dwarf galaxies in the local group. And that local group lies within the local supercluster, the Virgo supercluster. And then there's more clusters of galaxies. And as you keep getting like zooming out on this picture of the universe, we have what is called referred to as the cosmic web. So when you zoom out on the universe and all these galaxies form these like filaments essentially, and it looks like this cosmic web. And So our next student that we would like to highlight, whose work is kind of related to, broader broader distant universe or the big picture universe, is Evan Nunez, and he is a graduate student at Caltech. And his path in astronomy started when his mom took him to a library in El Segundo. He did grow up here in Los Angeles area in SoCal, and he wanted to check out two books. One was about Mars and one was about Venus, but his mom said he could only pick one. And at the time, he felt like this was the hardest decision he ever had to choose. And he read summaries on each of the books and was captivated by Venus because it had been before any like before we made actual observations with the spacecrafts that we sent there. People had imagined that Venus was a heavenly planet that was like luscious with waterfalls and vegetations and all these clouds, but then it turned out that like it was actually the closest physical representation to hell that we had ever found. It rains acid on the surface, and the clouds trapped so much heat from the sun that it raised the planet's temperature to where lead can melt on the surface. And that's where Evan, once he discovered this, was enamored with the diversity that's present in our solar system and got him imagining how diverse the rest of the universe must be, which I really love that because it kind of does go back to what I said, that like the weather within our solar system is so extreme, and it's just the universe is so extreme as well. Um, and from there, Evan was hooked, but he didn't really on astronomy, but he didn't really um, kind of like touch it again until an astrobiology course he took his junior year in high school that reignited his passion. And then he went to El Camino College, which is a community college in SoCal, and as a physics major, and earned 6 associate's degree, and then did summer research at the University of Wyoming and Cal Poly Pomona. He then transferred to Cal Poly Pomona and continued his research and did another summer research project at Harvard and earned his bachelor's in physics in 2019. And now he's at Caltech, studying topics that he's always been interested in. And so some of the work that Evan has done in the past as well was that he studied X-rays from young stars using the Chandra X-ray Observatory, and he's now currently studying high energy radiation from massive stars using distant galaxies. And continuing on with this is that he he's finding the oldest and brightest objects in the universe. So, how I said, it's more of like zooming all the way out to the earliest objects in the universe. That is what Evan is looking at. And he's looking at like these very, very early galaxies and modeling how these metals evolve in it over time. Should basically trying to get a good understanding of like galaxy evolution and the metals in the first stars, and how the universe was ionized from those first stars. The specific like area of research that Evan is currently involved is referred to as Galactic Archaeology. That's the research group he partakes in astronomy. If you have not heard of this before, it's basically um, the study of stars and galaxies, with studying the compositions and motions of stars in a galaxy to learn more about the galaxy's history. And so his group measures the motions of stars to learn about the structure of the galaxies and the nature of dark matter. And they also try to infer, they measure different amounts of elements and metals in the stars to try to infer the properties of the supernovae that exploded to produce them. How I said earlier. So this ties back to what I said earlier about you have stars can only produce elements as heavy as iron. Iron, anything heavier than that was produced in a supernova explosion. So that's what some of the work that Evan is currently doing and trying to do. So, as a brief summary, before I move on to the night sky show, since we are almost out of time, but feel free to ask any question. A brief summary of the tour of our universe is how I said you have Earth in our solar system, and we learned of some of the cool science Angelina did with Jupiter and Cassini, and currently does with Sun and the interactions with Earth's magnetic sphere. And then we had Dakota, a UCLA graduate student who also did some early work with the Mars winds. And then as you expand out, you get more star systems within our own galaxy with over 4,000 exoplanets and these interesting things called hot Jupiters, which they were a surprise to astronomers that Jupiter-sized planets orbiting so close to their star, and they're losing their mass, and that's what Dakota looks into. And then we had Jason, who is building a instrument to try to observe these very small changes in brightness from very far away distances to observe from Earth. Major contribution there. That's very exciting to for his instrument to be up and running. And then from there, we then talked about Ronald's work, which is also in instrumentation and trying to see if this warping of a disk is due to a planet. Sorry, excuse me. And then as you go beyond, beyond all the star systems, you have our galaxy. And within our galaxy, Leo, one of our UCLA grad students, found this filament that covers about three star forming regions, and also uh, l- looked into like the vertical motions of the galaxy and looked at the stellar populations on the outskirts of the galaxy and found that there is less like evidence for less stars being out there on the outskirts of the Milky Way. And so as you leave the Milky Way, you then enter the local group of galaxies with Andromeda near us and all their dwarf galaxies. You zoom more out, you get the local supercluster, the Virgo supercluster. And then as you zoom out, you have more and more clusters of galaxies. And what Leo also is currently researching he is currently researching is the metallicity, or how much elements heavier than helium are in galaxies around that in galaxies around 2 billion years after the Big Bang, which is known as cosmic noon, because these galaxies were forming a lot of stars, and this is the peak, like the peak time where star formation was at its highest in the history of the universe that we know of. And then as you zoom more out, you get these filaments of like galaxies, right, and clusters. And what Evelyn is looking at is at the first stars and the first at distant, very, very distant galaxies and the oldest objects in the universe. So please let me know if you have any questions and I can try to answer them. But I will now be continuing on to our night sky portion. I somehow managed to go a little over time. So hopefully I'll try to go as fast as I can with this, or still includes some cool stuff. But feel free to ask me to see anything you'd like to see on the chat. I will be using Stellarium, which is a free it is a free software that you can download online. And what is very cool about it is that you can input different times and you can go back and forward in time. Right now, it is set to Los Angeles and it is currently set to the current light pollution. So, as I mentioned, we do have a lot of in LA, in particular, we have a lot of light pollution. So civilization is here, and all that light does affect what you can see outside. Also, smog. And what's cool about this is that you can have light pollution, you can take it from the database, right? Or you can take it off and as you can see there, I kind of minimized it and now you can see more. But if I do so I'm going to increase because yeah, there you go. I feel like that's more accurate with what LA is. Maybe that might actually be too much based off what I saw the other night. Um, So what is up right now, and for sure I can confirm that you can see this from LA, is if you look to the south right now about this time, and you find the brightest object in the sky, you from there kind of want to look southwest diagonally, and you'll see Orion. So the Orion constellation is out and visible, and you can see it from LA. I saw it the other day while I was out eating ice cream. And you can also tell because you can see Betelgeuse. Betelgeuse is that orange star there. Um, and what's cool about this software too is that you can draw constellation lines and labels. So as you see here, because sometimes it's a lot harder to see, but on your own without the lines, but those three stars there form Orion's belt, and as you can see his arrow there, and that is visible in the LA nighttime sky. Even with the light pollution, you can see it now. And as I said, just look for the brightest star, Sirius, and then from there go diagonal. So let's see what else is like cool out here. If you have the chance to go to a dark sky, I would recommend. That's very awesome. I went like 2 weeks ago to Joshua Tree, and there you can see more constellations than this. So let's see, I'm going to go ahead and add these constellation lines so you can see them as well as constellation labels. So what also is out right now is you have the Taurus constellation, and if you ever find you have Virgo coming up, it's Virgo's rising, and what's a helpful fact is that whenever you are like do find one of the zodiac constellations, you if you look kind of like just diagonally across, you should be able to find more. That's because they all fall under what we call the ecliptic, a solar ecliptic. So the solar ecliptic is basically the path the sun takes throughout the year, and all the constellations lie on that same plane. So once you find one, you can find more easily just by looking in like the same direction. So for example, Virgo's rising right now, and then right above it, you have the Leo constellation. And then if you just look along that same line, you have Cancer constellation, Gemini, and then Taurus and Aries rising. So you just want to go right across them. Um, Another constellation that you can see is Cassiopeia. It looks like a W. So if you were to go out there without these lines, you would, again, Sirius is the easiest, and then Rigel, and then you'd want to look northwest. So essentially, this is a little challenging because it's not you. Okay, so you'd be facing this way, and you'd want to almost do like a 180 and look northwest. And Cassiopeia corresponds to like this W shape that you have there. It's easier with the lines. What else is out? Let me see. Um, I can also change it so that there's less starlight, just because this is essentially what you'd get at a dark sky if you were to go to a national park like Joshua Tree or anywhere out there around this time. Um, let's see. Oh yeah, we also have in you have Canis Major with Sirius, right? So once you look at Sirius, you find that bright star, right? It's connected to the Little Dipper, which is part of the constellation Canis Major. It looks like a little dog. When you first look at it in the night sky, I was with friends at Joshua Tree, and we were like, how did they get a dog out of that? But you have to, it's kind of like the Little Dipper forms a head, and then beyond that is there. And that's right next to Orion if you look up at the night sky. And if you were to see that, and then you'd have to, the Big Dipper should also be out. Let's see. Yeah, you would just have to kind of look directly overhead at this time. And this is a very hard thing, but you would see the Big Dipper. So what I can do is also fast forward, so I can play it in real time, right? And as you fast forward through the night, since this is right now current time of, um, as you fast forward, you should see them start to set. Okay, there you go. So it might be, how I said, a little harder to see the Big Dipper and Canis Major at 7 p.m. or 8 p.m. just because it would, personally for me, it hurts when I like look straight up. But yeah, so you'd want to wait maybe this is around, oh, 1 a.m. is when it's not directly overhead. And this you'd see here is the Big Dipper with Ursa Major right there, which is that constellation there. And then, as I mentioned, once you find one of the zodiac constellations, they just keep following. And here, once around 1 a.m., Libra will have risen, and then Cassiopeia will start to set. And just to wrap up, I have about like 2 minutes left. Another thing that I did want to mention, since we did talk about planets in our solar system, is that right now, given this time of year, there is not much, there, not many planets are visible. Jupiter, for example, rises at almost 7 a.m. right now, and it sets at 6 p.m. So I can go back in time if you go here with the cool part about this, how I said you can go in different times. So let me go to, let me do, oop, to, okay, no. So if you ever want to know what's up in the sky as well during different times of the year, the software is nice just because you can time travel with it. And let me do six. So it sets at 6 p.m. Yeah. So if you can see here, Jupiter should be around the horizon. around this time, but it's very hard to see planets at this time of year right now. And the other thing I did also want to mention, oh, that's probably because I so six, so yeah, sorry, I should do 18 to see. There you go. There you go. I had put it inputted the wrong time. So as you can see, around 6 p.m. when the sun's setting is where Jupiter and when Jupiter and Venus are setting. And Saturn, since we also discussed Saturn, Saturn rises at 5:46 a.m. So maybe that one, if you are like an early bird, might be able to see. Let's see. Well, yeah, it rises at that time. Let's do well, it starts rising, so that means it'll be on the horizon. And by the time by the time it starts to rise more to where it's visible, the sun's already out. And so those will come around. So you can see planets more later on during the year. And the other thing too that I wanted to mention that is visible right now, since we briefly touched upon it too, was Andromeda. So Andromeda is out in the nighttime sky right now. Let me just redirect the time. Okay. Yeah, so Andromeda is near Cassiopeia. So that's a key way to find Andromeda. So once you, again, you go brightest star, Orion, look over for the W in the northwest, and right below that will be Andromeda. So you can see Andromeda Galaxy. And if you do go to a dark sky, you can see a bit of the Milky Way too. As I mentioned, we are on like the edges of it kind of. So we have like this pancake view of all those like really nice pictures you see of the Milky Way. The only thing is that right now it's slightly visible, but it's better seen like around May, June, really good to see in July at like a dark sky. It's really pretty. Okay, so we're approaching past the time, but if anyone has any question, please feel free to like put that in the chat. Otherwise, I can also like show anything anyone else is curious about the night sky. And so I'll just like give it a few seconds. Um, okay, well, thank you everyone for joining and for watching and listening in. I hope you learned a bit about our universe and got a great tour of the universe and some of the really cool contributions that some of the Black astronomers and physicists within the Los Angeles area or from the Los Angeles area are contributing to the field right now. And as I mentioned, also, we will be having another show this week on Wednesday that will be in honor of Women's History Month. So tune in at 7 p.m. this Wednesday. Our two other grad students, Claire Williams and Nancy, will be hosting the show. And we also will have one again next week. Other than that, please follow us on Twitter or our Facebook page as well, and we'll update with any updates for next quarter. We decide quarterly what the shows will be like, if they will be in person or not. But thank you, everyone, and have a great night.